Hi, I'm Jake Sioka. I'll be explaining how to find Inviscid, laminar, and turbulent flow over a cylinder. To start, we're going to open up our geometry tab and get it on our XY plane and then open a sketch. First, I'm going to do some lines to get our boundary rectangle and make sure it's at the right dimensions. Alright, and next we can add a circle and then edit all the dimensions at the same time. We'll have dimension for the circle and then for every line. And then we can come down here, make our circle 1 meter diameter, and then every line will be 25 meters to create a rectangle of 50 by 50 meters. And now we can create our rectangle going from each endpoint. Then we can trim whatever lines we don't need. Alright, and then that's all the drawing. Lastly, we can make a surface from the XY plane sketch and generate that. That looks good. Next, we can come back, open our mesh. The geometry and mesh will be the same for all three types of flow. So I'll only show it once, and then I will just start from the setup for each separate flow. Okay, it's loaded. We'll start on the XY plane. First thing we can do is name all our edges. This will be our velocity inlet. We'll have a pressure outlet. And then our top and bottom walls will be just a basic symmetry. And the inner wall we'll just call wall or cylinder wall. Double check those are all right. Next, we'll start our meshes. First mesh is going to be a method mesh on our face, and we're going to change it to be a triangle. And we can update that so we can see what it'll look like. It looks like this to start. Our next mesh will be a sizing mesh, and we're going to do it along our inner cylinder wall. Inner cylinder wall, we're going to make it a divisions, and we're going to do 200. And no curvature, and behavior is going to be hard. Alright, we can generate this and see what it updates. It'll just make it a little finer around the inner cylinder, which is important, so we get proper values. And then our last mesh will be an inflation mesh, but I'm going to do it without a growth rate just so it gets more finer. Our first geometry is just going to be the normal face, and then our boundary is going to be the inner wall. We're going to do first layer thickness as 0.003. Maximum layers, we'll do 200. And we're going to keep it as a 1 growth rate, so it's equal all the way out to that 200th layer. and that looks right. And before we update that, just so it saves a little time, we're going to change our element sizing to 0.1 all the way throughout the mesh. And this will take some time to generate, so I'll cut back when it's done. Okay, the meshing's done. It appears just to be a black square, but as we get in, we can see how fine it is. This is due to the 0.1 element sizing in our main mesh. And then as you can see, this is what happens from our inflation mesh, where it just creates a bunch of tiny rectangles, 200 layers of it, starting from that inner circle. This is super helpful to get more accurate results as you're mainly analyzing what's closer flowing around the circle. Now that that's done, we're going to exit and enter the setup phase. You can generate this or update to make sure it works. Okay, I'm going to be opening up now my Inviscid flow. I've already completed this, but I'll just talk through all the steps from starting at the setup now that the geometry and meshing is completed. You're going to want to do as many solver processes as you can in double precision. I'm using a free version, so 4 is the maximum of solver processes I can use. Okay, now it's loaded. I wanted to show, you can see here that our mesh created a little over 500,000 cells, which is a good amount that you want to be shooting for. First thing I like to do is come to results and residuals. You can update your residuals. I chose e to the negative 5, or 1 times 10 to the negative 5. Next, since this is a Inviscid flow, I made sure to change my model to Inviscid flow. That's the only thing you need to do here. Everything else should be off. And then materials, I chose a density of 1 just for simplicity. Boundary conditions, your inlet. This is where really the only thing that changes for Inviscid flow, because you have no viscosity. I chose a velocity of 5 meters per second. And outlet, this is your pressure outlet. Prevent reverse flow, you sometimes will use, but not for this project. And just a normal absolute pressure. We can check our reference values, make sure everything is updated right. So I'm using 4. That's what I actually did for my main project, so we can update that here to be 4. And to update the reference values, make sure everything's right. You compute from your velocity inlet. Everything looks good here. Next thing you can do is come to methods. Now, originally it'll be a coupled scheme and pressure will be second order. Only for Inviscid flow, you can change it to simple and presto. This will just help speed up the calculation process. For other flow types, I tested it and it just wouldn't work right, and my graphs just came out wrong, but for Inviscid flow it still works. Monitors, you can double check your residuals here, and we'll come back to this to find our drag coefficient from the plots. But first we can initialize, get our first 10 initializations, and then we can run the calculation. I was doing about 500 iterations to 1,000. I'll probably just stop this around 50. But downward curve, it'll drop off. Sometimes it'll start spiking and going up, but that just kind of happens with cylinder flow. I'll stop here just to save some time. First, we can come to our plots. You're going to want to create an XY plot with pressure and change it to find your pressure coefficient along the cylinder wall. It should look symmetrical, and this looks right. It's two lines, but they're overlapping perfectly, which means it was pretty accurate even under the 50 iterations. Next, you can come to your report plots, new definition, force report, drag. This will give you your drag coefficient again along the cylinder wall. You can compute this. It should be super tiny. This is mine, so almost zero, not almost, but very tiny. For ideal Inviscid flow, it should equal 0. Now that is completed, that is everything we need to do for our setup, and we can now go to our result tab. Okay, now that we're in results, you want to get on your XY plane. You're going to be doing, for our project, 2 different contours, a pressure contour and a velocity contour, which you can make from up here. Once you get one going, you want to change the location to be through your symmetry 1. This will be my pressure contour, so my variable is pressure, and then I did 110 contours just so there's a little more diversity. And we can see that here, for Inviscid flow, everything should be very symmetrical, which it appears to be. Next contour is your velocity contour, very similar, but the variable will just be your velocity. Again, should look very symmetrical, where you have low velocity right at the left and rightmost edges, and your max velocity is up here where it's acting as a nozzle, and on the sides where they're acting as diffusers. You can better see this when you make your streamlines. Up here, you just create a streamline, and you choose to start it from your velocity inlet, and I chose 500 lines. That seems like a good spot. It gets the point across. Variable, velocity, and it looks something like this, where you can see again at the top and bottom it's acting as a nozzle, increasing your velocity, and as it reaches the cylinder and leaves, where these are equal because of Inviscid flow, this is your lowest point in the velocity, and everything else is pretty much just straight lines. That is everything we needed on this project. The next videos will be covering laminar and turbulent flow.